Well, good evening, everyone. Thank you very much for the introduction, Corey. That was very kind. And it's my pleasure to be speaking to you from beautiful British Columbia. First, I'd like to gratefully acknowledge my co-authors, particularly Tristar Gold, for allowing me to present this material and allowing this material to be shown. After some conversation with Corey, we decided it would be best for the DREGS group to benefit from a little bit more background in machine learning, and a little bit less sort of nitty gritty about the Castelo de Sonhos deposit in Brazil. So you'll notice that the title here has changed. From the one that you saw in the newsletter, but don't worry because we'll still be talking in depth about the Paleoplacer gold deposit, and we'll lead into it a little bit more gently with some practical applications and examples of machine learning in mineral exploration. So first we'll do a quick crash course in buzzwords. What my goal here is to demystify machine learning and artificial intelligence in machine learning and 3D modeling. But the first thing I'll do, unfortunately, I suppose, is to introduce a new buzzword, which is geodata science, which is sort of a hot new term, and it's being applied to geoscientists who know just enough about data science to be dangerous. Then we'll talk about the case study, which is the chemostratigraphy of the Esperança South Paleoplacer gold deposit, which is in Castelo de Sonhos in Brazil. And within that case study, we'll talk about multivariate analytical techniques like centered log ratio, principal components analysis, clustering, and discriminant projection analysis. And then we'll finish it up with a couple of key takeaways. Before we get started, I'd like to give you just a really quick overview about Goldspot Discoveries. So Goldspot was born out of the 2015 Integra Gold Rush Challenge. And if you're not familiar with that, because it was 5 years ago or because it was in Canada, the Integra Gold Rush Challenge was this company, Integra Gold, released a 6 terabyte digital database, which was a compilation of mining and exploration data from their Sigma-Lamaque mine in the Val-d'Or region of Quebec. So they released this data into the public domain. And then anyone was allowed to download it, and cash prizes were awarded to the group that could point to the next big gold deposit on the property. So first place went to a group called SGS Geostats, and that's a professional geological consulting group within the SGS corporate umbrella. But second place went to a group of students called the data miners. And then some guys with some money went to the students and said, do you want to do this for a living? And Goldspot was born. So today, Goldspot has grown into a group of over 30 professionals. It's a technology company and a consulting group which combines geoscience expertise with numerical processing expertise, and in that way brings data-oriented solutions to the field of economic geology and mineral exploration. So you can think about it as a company of AI-assisted exploration geologists who work across a series of different commodities and mineralization styles. So the first three caveats of artificial intelligence in mineral exploration are that mineral deposits form for a reason, and that reason is related to geology, that machine learning can process geological data to discover patterns, and that machine learning derived products support exploration. So they support finding targets or looking at new exploration regions. So here we have our example of data mining. We have these guys and they're mining this data. And at Goldspot, we try and bridge the enormous gap between traditional geoscience and artificial intelligence. So we combine geologists and data scientists together, and we create hybrids like geodata scientists, like I just mentioned. And this is critical because geological data is not the same as normal numerical data because it's kind of soft, it's sort of squishy, and it has all of these baked in assumptions and conditions like error bars that are so obvious to the geologist, but they're not so obvious to the data scientist. So it's really important that we work together. So first we'll talk a little bit about artificial intelligence in general. Artificial intelligence is the computer-based reproduction of tasks, and machine learning is a subfield of domain-specific AI and can really be thought of as a toolbox of algorithms and techniques. Machine learning can be broken down into 4 major subdivisions: deep learning, supervised learning. I'm gonna look for my pointer. Yeah, deep learning, supervised learning, unsupervised learning, and regression. So if you go to YouTube and you look up what is machine learning, this is what you'll get in your first lesson. So machine learning is based out of basically two main topics: supervised learning, which is the use of a discrimination function based on prior observations. And the goal there is to apply labels to unknown data or incoming data. And then there's supervised learning, which finds grouping of data in high dimensionality space with limited preconceptions of how the data are arranged. So stepping back into something more familiar, back towards geology, we can reframe supervised and unsupervised learning in this way by looking at two simple two-dimensional plots. On the left, we have an example of supervised learning. So we have some input variables and we have some classification fields. And using geological expertise and experience, we can derive these classification fields. But on the right, we have an example of unsupervised learning, where we look at associations of two elements, in this case, titanium and thorium, in bivariate space, and we can find out some information about different rock types based on where they sit together on this bivariate plot. So these are great and they're incredibly useful, but this is just, two or three variables. What if we have 5 variables or 20 or 100 variables? So we can start with a pretty simple example of machine learning, which is k-means clustering. And I'm sure lots of you, or probably all of you, have seen k-means clustering at some point. It's very well understood and very well studied, and it's used to group data together by similarity. So traditional machine learning has value because it often gives good results with lower numbers of data points. So we can call that itty bitty data or small data or even large data. And these algorithms are often baked right into software packages that we use all the time, like IOGAS, for example, has had k-means clustering for ages, or even self-organizing maps. A slightly more complicated example, and this is deep learning here, when we're feeding hundreds of images, and on the top left we see all these different images, we feed them into the deep learning algorithm and we ask the question, is this a dog or a cat? So deep learning is a little bit different because it's not really a one-off solution that you can just apply everywhere. Like you can apply k-means clustering to any type of data, really. But a deep learning algorithm is more specific. So it gets training points. And in this case, when it eats enough training points, and lucky for this dog cat example, we're feeding all of this training information freely from our own social media, the deep learning solution eventually can accurately predict dogs or cats. So in this way, we can use a deep learning algorithm, which takes a little while to get right, but after it's trained properly, it becomes sort of set and forget. So here we just saw these two examples of machine learning algorithms and with completely different applications. And there are thousands of different algorithms out there. So the secret sauce to knowing to doing machine learning correctly is knowing which is the appropriate application for each algorithm, because it's just math and everything is just publicly available and it's all documented in the public domain. But to do it right, expert knowledge is essential for success. So before we get into the meat and potatoes of the case study, I'd like to show you just a few examples, relevant examples of machine learning in mineral exploration that will kind of get everyone's creative juices flowing. So first, how do AI and machine learning add value for geologists? Fundamentally, we need to interpret geology to explore for mineralization and ore deposits. And to do this, we consider how geological data relate to one another by making maps and models. So a problem that we come across all the time is this data deluge, where we have a whole lot of data and it's a whole bunch of different types of data present. Trying to integrate that data manually can be, at worst, impossible, or at best, not efficient. So this is where machine learning enters the picture, because we can think of it as domain-specific automation or pattern recognition. When we use it well, machine learning can provide automation, which improves time and cost efficiency. But the other bonus is that it adds consistency to our results. So, and this is just my opinion, but I don't think that the technology can stand completely on its own without a geologist involved, because of the nature of geological data. It's squishy and kind of unconventional, like we mentioned before. Instead, I think the real value comes from improving the ways that we already work. So the dog photo example is a little bit abstract. So we'll go back to geology and we'll use this geological example that uses deep learning 2 separate times. And this is a Goldspot tool called LithoLens. So the first deep learning algorithm extracts data. In this case, the data is rock from the photo, from the old photo. And second, that another deep learning algorithm identifies and quantifies both quartz and iron carbonate veining and georeferences them in XYZ space using the collar and survey information. And the output here on the right-hand side, there, is a drill hole graph of vein density. And all of this has been extracted from historic photos. The cool thing is, once the deep learning algorithms have been trained, it can be used on thousands of meters of historic imagery. So for example, a model that we recently created takes about 0.6 seconds per photo, and 100 kilometers of drill core can be processed looking at 89 million parameters in just less than 6 hours. So of course, this isn't happening on somebody's laptop. This is all done in the cloud, but this sort of showcases the real power of using deep learning, is that you can extrapolate some of the more challenging things like looking at images and do them more quickly. Much of the really popular machine learning and mineral exploration is these prospectivity maps. So most of what you've probably seen in social media, for example, relates to these. And prospectivity maps are all about assessing the probability that a specific pixel has the same signature as mineralization based on input layers such as geology, geochemistry, or geophysics. And these can be made with either supervised or unsupervised algorithms. And the idea is to just jump straight into a drill program or a sampling campaign by creating this stack of geology data and then finding the best signals of the deposit that you want to find. So to paraphrase what I think it was Craig Hart that said, many deposits do not have huge expressions, therefore regional data may not be helpful. What we actually need are products that a geologist can use in conjunction with their own inherent knowledge of the property at the deposit or the brownfield scale. So this is an example, a mapping example of using unsupervised learning. The satellite orthophoto on the left can give us an idea of the terrain in the area. And in this particular case, the area is incredibly remote. There's no reliable boots on the ground mapping. But using hyperspectral data from Aster satellite, we can create a regolith map of the surface materials using unsupervised clustering. In this case, it was a self-organizing map. And that can guide our efforts on the ground when we do get a person out there. The next example is supervised bedrock mapping. So another kind of catchphrase is machine-assisted map making, and it's another hot theme right now. And this is an example of supervised learning applied in conjunction with a geologist. So on the left, we have our historic map. Then using many layers of geophysics data, patterns that relate to the different rock types are analyzed and interpreted. So finally, on the right-hand side, we see the resulting revised and improved map. And that map is used to support a variety of exploration purposes. So how would one start with machine learning, or where could I fit in? You may be asking yourself, you may not. And machine learning and artificial intelligence includes all aspects of geoscience. So certainly these tools aren't meant to replace geologists. I mean, data science is a new discipline, just like mapping was a new discipline and resource estimation was a new discipline. And the workflow includes all aspects of geoscience. So on the top, we have our Chief Technology Officer, Sean, and Vivian, that we were speaking about earlier. And they're in the field and they're thinking about structural geology. And then next we have one of our project managers and an excellent field mapper, Mireille. And below we have one of our data scientists, Vero, but the take-home message from this slide is that they're all thinking about and working on geoscience problems. So in machine learning itself, there's two types of learning curves, kind of abstract learning curves, the shallow and the steep. And on the bottom, we have a whole bunch of different logos from open source machine learning software packages. And you can go and grab one of these packages right now. Some of them are free, some of them cost money. And you can set out to become a machine learning geologist right now. On the left, we have the easy learning curve, so something like iogas or orange are relatively straightforward, no coding necessary. But as we move from left to right, things get more complex until we arrive at what we can refer to as the ultimate end member, which is coding only. And if you want to code, then certainly the learning curve is steep. Another way to think about this is as end members of experience. So for example, here are three of my colleagues. This is Lindsay on the left-hand side, and she's a field legend. She's worked for the Ontario Geological Survey, and she has international mapping experience. In the middle, we have Vincent, our CEO, and one of the co-founders, one of those original students I was talking about. And he has knowledge of geology and data science both. And then on the right-hand side, we have Pejman, and Pejman is a data scientist. He's a geophysicist and a statistician. He lives inside the DOS window, and he doesn't go to the field, but he does have a very excellent story of one time he was in the field and he got led home by a donkey in the mountains. So Pejman does go to the field, but most of the time he's in the DOS window. But what I'm getting at is that it's a continuum. So we have our field geologists or pure geologists with strong geological foundations, and they understand data collection and they understand data organization, and they can identify good versus bad data and good versus bad interpretations. And then we have our hybrids in the middle who know about general geoscience, but also general data science, and they can guide geological data selections, and they can assess results in terms of machine learning and geology. And that's really important because something that people tend to forget about is that machine learning will always give you an answer, but it's up to the geologist to assess whether or not those answers are correct or whether those results make sense and to validate the sanity of that answer. And so it's just about thinking about what works best for your organization and your people. I mean, does it make sense to stack out your team with a bunch of pure geologists or to stack out your team with a whole bunch of data scientists? I believe that it's best to sort of shingle your skill sets together so that there's overlap between all of your team from one end member to the other, which takes us into the Castelo de Sonhos case study. So I've called this spoiler alert because I'm going to tell you basically what I'm going to tell you in case anybody feels like falling asleep. But the purpose of our work, and when I say our, I mean Goldspot's, the purpose of our work at Castelo de Sonhos and in all of the projects that we undertake is to find more gold. Specifically, we predict where gold is going to be. So at Esperança South, a Paleoplacer gold deposit, it's one of the most interesting projects I've ever had the opportunity to work on because it's so well endowed, but it's also so unique. I'd never worked on anything quite like this before. In sedimentary rock hosted deposits, the controls on mineralization are primarily due to the original depositional environment. So knowledge of the detailed stratigraphy is critical for building reliable models. On the left, we see the original first level field mapping geological map. And on the right, we have our completed three-dimensional geological model. At Castelo de Sonhos, the ability to accurately predict where gold will occur and will not occur critically depends on the sequence stratigraphy. But this was always the biggest challenge at Castelo de Sonhos because the metasediments are all sourced from similar host rocks, and it's a series of repeating and overlapping sequences that in many cases are only distinguishable by very subtle changes in texture. So this is a really, really hard deposit to log. So the Tristar team, they used a whole bunch of really excellent and really well-validated approaches. They signed the option agreement from Barrick here in 2010. And so they've had the project for about 10 years. And over the course of that time, they had some outstanding work from some world-class sedimentologists. And they did some extensive regional geophysics, which was super helpful for us. And we'll talk about that later. And they also pulled some tools out of the oil and gas toolbox, like optical televiewer and some detailed petrophysics. But what was really interesting at Castelo de Sonhos, what really cracked that nut was geochemistry. And specifically, it was strong acid. So Tristar has a huge collection of gold assays from across the project area. And when we got involved, when Goldspot got involved, they were just starting to routinely collect aqua regia data as well. So after looking at that preliminary aqua regia data, I suggested that they try out 4-acid digest on just a few holes. The C-suite at Tristar agreed, which was huge of them. This was an incredible decision and turned out to be a really critical decision for the project, and the results were promising. So they analyzed a few more holes, and the results continued to be promising. And what they have now is this critical chemostratigraphic model, which has allowed them to make better predictions of the sequence stratigraphy and therefore improve their exploration targeting. So the Castelo de Sonhos project area is located in the Para state of Brazil, in the northern part of Brazil there. And as you see in 2014, they had the earlier parts of the mineral resource in Esperança Central, Esperança East, and Esperança South. Then by 2017, they had upgraded the resource. And in 2018 as well, they had upgraded the resource again. And in 2021, they're looking to upgrade the resource even further. It's a paleoplacer gold deposit, as I mentioned previously, in a paleoproterozoic conglomerate sequence, and it's 2,086 million years old. So we care about paleoplacer gold deposits because they're a really good place to find gold. 40% of the historical global gold production is from paleoplacer gold deposits like the Witwatersrand Basin in South Africa and the Tarkwa Basin in Ghana. Generally, they're formed by these processes in sequence. So first we have the formation of an early granite greenstone terrain. Then there's deformation, including uplift and erosion to develop an unconformity. Then there's extension and rifting in developing a basin. And finally, there's compression, including thrusting and uplift and erosion of the granitic margins. Paleoplacer deposits consist of concentrations of fluvially deposited minerals like gold or uranium, which are then consolidated or cemented together by burial processes. Gold is present as discrete grains, and the host rock is commonly a quartz pebble conglomerate. The gold deposits are found specifically within fault-bounded depositional basins, and the periphery of these basins commonly consists of granite greenstone terrains, which are the source of the lode gold and the detrital material infilling the basin. The gold reefs are typically located along unconformities or at the top of sedimentary beds, and the mineralization style is pyrite-bearing quartz pebble conglomerates and quartz arenites with variable hematite. So now that we all feel super comfortable with paleoplacer gold deposits, we can refocus our attention back to Castelo de Sonhos. So we have our original geological map here, and it's a very good map. It's really functional, but it's the detail is relatively spatially limited to this area and insufficient for regional exploration. So we have the metaconglomerate here in hot pink, and we have the meta sandstone beside it and around it in yellow, and it's all encompassed by this granitic unit here. In the center here, we have our location map showing Esperança Central, Esperança East, and Esperança South, and we're going to be focusing our attention in Esperança South, because in 2020, Tristar embarked on a significant infill drilling campaign to better delineate the stratigraphy at Esperança South. And the purpose of this was initially to upgrade the resource classifications, and initially the geochemistry was only meant to be gold only. But this dense infill drilling had another boon attached to it that was at the time unknown, and it allowed them to collect a vast library of really high quality geochemical data that then facilitated this chemostratigraphic sequence mapping of the sediments across the plateau. So this is an example of one of the earlier cross sections at Esperança South. We're looking north here. We have west to the left-hand side of the screen and east to the right-hand side of the screen. And you can see that it's tricky. You know, we have many layers, and a lot of them are more like lenses, and there's not a lot of continuity, and they pinch out all over the place. And on top of that, we have the challenge of trying to model this nuggety gold deposit. So you can imagine what a nightmare it would be to try and model this or create a resource estimate. And then along comes geochemistry. So the upper image we have here is the original visual logging, and then the lower image is the chemostratigraphy for comparison. You can see in the upper image that the sequences repeat and there's not a lot of continuity between the drill holes. So you can imagine how exciting it was for the Tristar geologists to be able to see, even from these preliminary results, that they could start to draw lines across a few of the drill holes and connect the dots. And you'll see also as well in the legend that our naming scheme is quite chemistry heavy. It's very chemical. So now we can get into the guts of the geochemical part, and this is an overview sort of summary slide of the months of infill drilling and analytical work that came next. So starting in April 2020 with the Algorit data from 3 holes, there was some success with the preliminary work, and Tristar were encouraged. So they sent a few pulps that were already at the lab for acid digestion on our recommendation. And these results were also promising, so they continued reassaying that data, and now the data set has expanded to include over 500 drill holes. So broadly, the geochemical workflow can be divided into 2 steps. The first step, which I was calling the global workflow, is to identify the main geochemically distinct units. And the second step is what I call the refined workflow, which has a separate dimension reduction step, which was UMAP in this case, followed by a clustering analysis, and that was to differentiate within the main sedimentary pile. So now we're going to get right into the nitty-gritty of the geochemistry. And for those of you that don't love geochemistry like I do, feel free to just tune out here. And then when it's time to tune back in, I'll say the magic word, and the magic word today can be pineapple. So as I mentioned before, we have these 2 workflows. We have the global workflow to identify the main geochemically distinct units, and then we have the refined workflow to differentiate within the main sedimentary pile. Once this is done, though, this is where the machine learning part comes in. I can take these manual Britt workflows that I created and bundle them up into a supervised machine learning algorithm. And in this case, I used a hierarchical random forest classification that can be used and reused as more strong acid data flows in from the ongoing infill drill program. So starting with workflow number 1, the global workflow, we have our regular data treatment like data cleaning, QA/QC, and then we calculate the centered log ratio of our input variables because of its compositional data. We can talk about compositional data later. And then we go through our first dimension reduction step, which in this case was a principal components analysis. And we start to see these interesting end members fall out of the data, like this. So we have our high field strength elements over here, our zirconium and our hafnium and cerium and lanthanum, for example. And then we have tin over here, which is we're thinking about maybe a weathered granite in this case. We have nickel chrome down here, cobalt, so that's going to be our mafic unit. We have iron and titanium over here, and our alkalis over there. So we see still that even though our initial legend makes a little bit more geological sense, it still has very chemical names, which is normal, because the next step will be to corroborate with the site geologists and start integrating the traditional lithological logs and help refine as well as give appropriate geological names to these geochemical names. And what's interesting as we continued to receive more data, the second granitic unit, which we previously had identified by its high potassium, now has enough samples to create its own pole in principal component space. So previously there were too few samples to really identify granite 2, so it didn't form its own distinct group. But now that we have more data, it starts to really pop out on its own in the PC plot. So on the top left here, we have one of the a little bit less data and one of the more original data transfers. And we see here, we do have a niobium tantalum pole, but there's just not much data associated with it. It was there before, but it kind of just looked like noise. And then we continued getting more data, and the data that we were collecting was in that region of the deposit. And then it starts to stand out on its own as its own, tantalum niobium granite 2 pole. And this was quite funny because I remember a meeting that we had with the Tristar geologists towards the end of last year, like in the fall of 2020. And they were jokingly but seriously asking, like, how many more times are the clusters going to change like this? And I had to laugh at it, and I said I was sorry, but we don't really know, because originally the clusters will look, let's say, quite chemically different. But then as we introduce new data, some that looked quite similar to each other, then will start looking more different, whereas others that looked similar to each other might look more similar to something else. So especially in the kind of exploratory data analysis part of this work, defining the clusters is very much a moving target, especially as you add more data from a different part of the deposit. So moving on to the second part of the workflow is the refined part, where we're trying to differentiate within the main sedimentary pile. And the first thing we did using the global workflow was to pull out our geochemically distinct end members, and then we're left with this sort of geochemically indistinct sedimentary pile. So we did our data treatment again, like our centered log ratios, and then we're doing dimension reduction a separate time, but this time we're using UMAP, which is a manifold learning technique. And manifold learning is sort of a fancy way of saying nonlinear. And then we go back and we cluster. So we tried a few different clustering algorithms in this case, like optics and DB-scan and agglomerative and fuzzy C-means, for example, as well as different metrics, distance metrics for each, including Canberra and Euclidean and Manhattan, and some different scalings. So you can imagine we have a whole bunch of different outputs to evaluate, but how do we choose which one is correct? Of course, we map it spatially. We put it into our geological model, or we put it into 3D space and we evaluate them. So at the right-hand side, this shows UMAP dimensions on the X and the Y axis, and this is the agglomerative result versus the fuzzy C-means result. Those are just two different clustering algorithms, and they look the same to me, for sure. They look identical to me. But on the left-hand side, we have the same results, and we see, if we look kind of carefully, it's subtle, but we see a distinct variation in the continuity of this pink cluster, cluster 2, through here. So if we were just looking at this in machine learning space, we would say one looks as good as the other, but it's really important to come back to your geology space or your physical space and assess the groupings. Do they make sense chemically? Do they make sense spatially? So now that I have my main sedimentary pile clustered appropriately, I have to interpret my groups and I have to give them names. So we see on the top right, we have this aluminum versus scandium plot, and this red group appears to have relatively less aluminum and relatively less scandium. We have aluminum on the x-axis and scandium on the y-axis. But if we look at the box and whisker plots on the bottom, we also see that it has less titanium, it has less potassium, it has less of pretty much everything, which means, because it's compositional data, that it has to have more of something else. So what is this something else? This something that we don't know about, this something that wasn't reported. It's 4-acid data. Yeah, that means it was silica. So if I had textural information, I could maybe call this a clean arenite, for example, or clean silica. Because I don't have textural information, I just called it a quartz clastic. And then I look at the variability of other elements, and I look at the logical logs, and I'm able to give relevant geological names to the rest of my unsupervised clusters. And then this is the final result. So we have our final merged workflow of our global workflow together with our refined workflow here. And we see first our granite in light pink up there. And then we see our upward channel sediments in light orange. And we move down into our iron sandstone conglomerates, and then our lower sandstones down here. And finally, on the other side of a question mark fault, we have our tantalum niobium granite over here, as well as our weathered granite unit at the top. And so here we have our completed geological map. And this geological map is what we can use to predict the location of our gold-bearing units across the entire plateau. So in summary, we have, turn off laser pointer. Play. Yeah. There we go. So this is our original field geological map. And we're starting with the regional geophysics. So that's the radiometrics and the magnetic intensity. And then this is the clustering of the radiometrics data. And now we're going to zoom into Esperança South. And we start to see the drilling data with the geological logging on top of it. That's the visual geological logging. And then we back out and we'll flip over to the chemostratigraphy. And from the chemostratigraphy that we see here displayed in the drill holes, we use control points from the surface model to create our geological model. So first we saw the granite bowl, and now we're looking at the overlying stratigraphic units. So then we back out, and we'll look at the radiometrics again over top of our geological model. And then we look at the clustered radiometrics here, and this is what we used in conjunction with the drilling data to make our geological map, which is helpful for exploration. Now this, together with our drilling data, becomes our geological model, which is helpful for exploration as well as mine planning, feasibility, and resource estimation. And finally, we'll look at a section here, which is a northeast-southwest section, which demonstrates the sort of bowl nature of the sedimentary basin. And as drilling continues, we can incorporate some of that new data into the classification scheme and into the model. So all of the upfront energy has already been expended, and now we can just sit back and enjoy the fruits of our labor. So the purpose of all of this was to predict where there's going to be gold. And in sedimentary deposits where the controls on mineralization are because of the original depositional environment, knowledge of that detailed stratigraphy is critical for building reliable models. So at Castelo de Sonhos, the introduction of this strong acid data was critical in the success at chemostratigraphy. And then just a couple of other kind of closing notes are always remember to validate your multivariate or machine learning interpretations spatially to make sure they make sense. Of course, collaboration with site geologists is key, and that the best weapon in your exploration arsenal is a robust and reliable geological map. Some references. And again, thank you very much to my co-authors and the co-contributors, and thank you to Dr. Viviane, who created this geological model, and of course all of the Tristar team. This is couldn't have been done without their input. So thank you as well to yourselves in the Denver Regional Exploration Geologist Group for your attention.